This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
So what's Daniel talking about?
This is about reading your mind.
Oh, great. That'll get people interested.
Well, but it's actually, I don't know the date or the, I don't know, it's not, has not that many registrations yet.
Oh, right.
And also Peter's.
So that's next week, is it?
That's next weekend.
Yeah, it's still a way off holidays, so yeah.
Then after that, there's a 2 weeks break because of the holidays. And then,
Oh, yeah.
but maybe people are already away. Not yet back.
Oh, yeah.
But those two around the holidays are not. At least he's always.
He works with David Simpson.
Oh, right. Oh, yeah.
Because he's always taking when David is away. He's
Oh, yeah, I know the guy.
he's done some biomet.
Yeah. Couldn't remember.
Yeah. Let's see if he's talking.
Yeah. See if you can read Roger's mind.
Well,
You
what
can
I
change
said
it in
was
5 seconds.
Yeah, maybe I learned something. Just apply that.
So do you know what sort of people are coming along?
I only know the ones that my kids brought.
Ah, right, they're friends.
They have like distributed in their school, and they don't know what otherwise.
Some parents come on too. There's a few parents or
Yeah.
audience.
Do any teachers come?
I think last time there were some teachers.
Yeah.
They talked to Roger, but otherwise I don't know. But I just got a list from Jacinta, like emails that I sent it to, and then I sent it to all the schools I kind of Googled.
Oh, yeah.
And it is recorded, so if you could wear that.
Oh, yeah, no, I usually do anyway. You don't know who
It's
needs
still, yeah.
some extra support there. I better get this thing talking as well.
Probably be 50 minutes this time.
Yes,
It's about 50 minutes, your lecture?
Oh, yeah, I'm a bit worried it's too long.
Well, don't be worried, because last time it was 1.5 hours or something.
Yes.
Who was that?
Roger.
So they're used to that.
Rogers. It probably doesn't seem like an hour and a half. I've got a dinner reservation at 7, so I need to.
So you have to.
All right.
I'm motivated to get out of here. Oops.
So you're on laptop wireless, aren't you?
No, I'll have to plug in when it gets to that
Yeah, you
point.
got the...
Oh, I have these. Everybody can grab one of these on the way in. And I've got some stickers afterwards. These are like our centuries. That's why I wanted to, it's good to know. You're the right people coming.
It's so hard to tell, because I mean, people register and then they don't come.
It's really cold today too.
Yeah. That's why I thought maybe next year make it more like first semester more summertime, because then it's not dark and it might be nice.
Yeah, more people might come in October. after the holidays because I don't.
It's closer to the EC exams.
Oh yeah.
That's the other thing. That's why I don't know what is the time.
Yeah, I know. Look, we've had these conversations for aeons. What's the best time to run things? People have got into the habit of coming to the July lectures. So
Yeah, that's a good. Apparently good. That's not also early because, for example, my son's school they all have done their choices already for subjects. So I think it's maybe better to do like early in the year before they do their choices because then maybe more choose.
It's for year 9 or something rather than
He's year 10 for year 11, yeah.
So what schools you go to?
Allen Park.
Oh yeah. So Rachel Gord was a teacher there. She used to be here. Everyone knows Rachel. Yeah.
She's a brilliant teacher.
Yeah.
I think. Yeah, I emailed her because I knew that she got a response. So she was distributed to her missing students or I guess students, whatever she's doing.
Yeah,
So you know her from what? She was
She was a student here.
a student.
Yeah, I think she did. She had done a master's or honours or something. I can't remember how long ago it was. It was a while ago now.
Yeah. But she's a really good teacher. She also got an award for best. This maths teacher was.
Yeah, no, I think she's obviously very committed. Yeah.
Yes. There's also refreshments upstairs if you want to.
Oh, okay.
Something, but
You can come here and go up and around.
either way. You can also open the door. It was just closed because it wasn't open.
Oh,
You can go up out the back and around.
Okay.
So where are the refreshments? Just there or
Just there,
further
just
around?
down, yeah.
thank you.
Where were you? Which school?
Junior high.
Oh.
So we did this thing in North Melbourne.
That it was in the name? Is it the name
It's a
of the
school, yeah, it's a local school.
Oh, lucky you.
Yeah.
It's so hard
Well,
to
we
get in.
used to live in Flemington, but then it was all getting, the house was getting too much for us, so we were going to do a major renovation. And we thought, let's just, we hated gardening too, so we did it. And the kids have moved out, so we've got partners and children. They've got two arts degrees. But Max is now doing Master of Science in Earth Sciences here, doing rock art, Indigenous rock art.
Okay.
So I've had to get used to all this sort of doing stuff with talking about doing run spectroscopy.
You bump into them sometimes?
Not really. And the other one's doing a master in teaching at Deakin. But she's doing it remotely.
Okay.
But she's just finished teaching around.
I think you said that she's in Derby.
And a school, there's some newish school in Werribee, so she's finished that now. She really liked it.
Okay.
It sounded a bit wild, but
Yeah.
I don't know. It might suit her actually. But she's very passionate about sticking up for the light. She was talking about trying to keep getting into trouble because he had a hoodie underneath his school puffer jacket. That's where they're trying to get kids to come to school, and then they start going, it'd be better that you come to school not wearing uniform. Just any barrier you put in place to stop you coming to school is huge. So, which seems very reasonable. Uni high had no uniform.
Yeah. One of the only schools I think here that I have not heard of it. Only the art school. I think that otherwise
So you're legit. Do you think wear uniforms? No, well, the primary school, there kids are primary. They had uniform. They just wear a hat when they go on excursions, and I think they quite like the jumper or something. But beyond that, it's very
I think primary school they're all a little bit
relaxed.
yeah.
That's fine with that. Yeah, people kind of if they don't have uniforms, they'll be competing for that clothes. You see the big high things, and they're all wearing jeans and hoodies.
And also they have their phones with they're competing with phones, shoes.
Yeah, these are these other things. Someone said, if you didn't have uniforms, it'd be people look at what car you come in with.
Yes, definitely. That's it.
You can't
Uniform
escape
is
it.
not the.
You can't escape it.
And they're really so strict about it. They're so uncomfortable, I think, often, and they don't look good. And teachers should wear uniform drama. Same thing that doesn't fit, and I don't know.
At the school I was at, my sister was in New Zealand, it was a government girls' school in Sydney. We had a uniform and they were quite strict, and there was one of the mistresses would come around and tell people off for not wearing the uniform properly. In the winter, we had a winter uniform, and part of it was wearing what they call flesh-coloured tights. Really, but people didn't want to wear flesh-coloured tights because black tights are much more fun. Anyway, there was this girl in Louise's year, and she's now a very famous artist.
Okay.
But she's Indigenous. And so when she was wearing black tights, and she got told, you know, you have to be wearing flesh-coloured tights, and she said, my flesh is black. And then that was the end of the point. That was the end of the conversation. Yeah, so oldie, she's quite famous.
Okay.
Alice and yeah, that's good. So you got Daniel. Oh yeah, that'll be our quantum sensing box. David, Harry. Yeah, Harry will be talking about light a bit too, but I'll just whiz through. Yeah, I'll mention photons, but it really won't.
Yeah, so, I mean, also not everybody can start with lecture on everything.
No.
Should I get them in?
Oh yeah, I probably should put the microphone on. Everything going okay with first year?
Yeah, they haven't rang me, so.
You assume it's all right?
Yeah, nothing much goes wrong. He's only there in case someone needs first aid or a bit of paper in the printer or something like that. But
First aid, is that much of an issue?
nah, I've only had to drive someone home once. They twisted their ankle in the stairwell.
Oh, okay. Did you have to fill out lots of forms to do that? To drive someone home?
I tried ringing in my taxi, but they never turned up, so we were waiting around for half an hour. And I said,
Are they
"Where's
far
it?"
away?
No, they were just in the city, so it wasn't too bad. I was sort of help them into their building. But apart from that, that's the only thing, really.
Who's in charge of the lab tonight?
There was a few demonstrators, but I can't remember their name. There's about 3 classes going at the moment, so. Okay, yeah.
Looks like almost could be as chaotic as last week. This week, or not quite.
No, it won't be.
Who was last week, Roger?
Roger was last week. You don't know what he's going to do next.
So apparently Roger's lecture was an epic.
Yeah,
Yeah.
I don't know the details of it.
yeah.
Hopefully mine won't be.
I videoed the ball rock when he stood up on the desk.
All right, oh, yeah, yeah.
Just so you want to start right away. Prefer, do you want to, that I introduce you, or you want to?
Oh, whatever you do normally.
Well, there's no normal for me.
There's no normal. Okay.
All right, I'll be sitting down the front of you.
Okay, great. Thank you. So should I plug myself in, or do you want people to just look at the schedule? Did you want to say anything about what's coming up, or?
I would just say that there's more lectures otherwise.
Okay. I'm just waiting. Should I plug myself in?
Yeah, how about do you want to plug in here, then I plug in the other one, and then we can just share?
Yeah. Yeah. So that's me. Your HDMI. Oh, there you are.
I never know which one's which.
Let's do that. I know, it's confusing. Yeah, the colour's not quite right on this one, but
So you are wireless.
yes.
I mean, just for the start, and then we can do it all yours.
Okay, that looks all right. And let me just check this. Oh no.
Battery or
No, it just sometimes
is
gets
it
stuck.
is a pointer?
It is a pointer. No, well, I just want this to work, that's all. So I can see it on there, actually. I will. If I do this, will that work? Yeah. It's just gotten into this weird mode. So, do you want me to?
Say a quick hello. I could say a quick hello.
You could say a quick hello. Okay.
Okay, welcome everybody to our gymnasium lectures. It's a series of several physics lectures. There's one more next week and then 3 more after the break in October. Today, for our second lecture, we have Professor Anne Roberts here with us. She is a professor here at the School of Physics, and her research area is optical physics. And she's also a chief investigator in the Center of Excellence for Transformative Meta-Optical Systems, right?
Yes, absolutely.
So I'm very excited to hear from her with her lecture today about optics, the future is matter.
Okay, thanks, Mary.
And for coming.
Thank you. So I'd just like to, good evening, thanks everyone for coming along. I'd like to begin by acknowledging the traditional owners of the lands where we are gathering. At the Parkville campus of the University of Melbourne, we're on the lands of the Wurundjeri Wurrung people, and I'd like to pay my respects to their elders past and present, and I'd also like to acknowledge the contributions of Indigenous people to science and engineering.
Let's just bring it back on both screens.
Yep, great. Okay, thanks, Steve. All right, so I'm obviously going to be talking about light. I'm also, if you look at some of the demonstrations here, we're going to make little detours off into talking about sound and waves. So hopefully by the end you'll see how all of these things link together. So basically I'm going to give a very quick overview of the history of how we understand optics, and then look at light as a wave, look at the phenomenon of diffraction, and then come back to looking at waves more generally and the concept of resonance, and that's why I have some of these other demonstrations here. And in the very last part of my talk, I'll discuss the field of meta-optics, which is what motivated the title for my talk, and it's a new way of thinking about controlling light by using some of the wave concepts, such as resonance, to be able to do things with light that traditionally weren't available to us because things need to be very tiny. So I guess a take-home in terms of the message here is really we're talking about the intersection of light science and nanoscience. So that's where we're going to be heading. Okay, so light is very important, and you might think, oh, you know, it's a very well-established field. Surely we know everything there is to know about light. It's actually very important for a range of reasons, and one of which is it underpins what's starting to be called the fourth industrial revolution that we are living through now. So the first industrial revolution involved the development of steam power and mechanisation. We then started looking at mass production, you know, widespread adoption of cars and other forms of transport. Distribution of electricity became very widespread. And a few decades ago, you know, computers became very widely available and a lot of activities became automated. What we're now looking at are things like artificial intelligence. We're looking at automated systems that integrate cameras, so machine vision is required. We're also becoming increasingly, people are increasingly using things like augmented reality to enhance their understanding of what's going on around them. So really, in this, what we're looking at now, we're talking about the digital world, the biological world, and the connection between these different types of knowledge is light, because it enables us to sense the world and use that information to make decisions and control various interfaces. And it's often said that more than 90% of the information that we obtain, and in particular if you think about human vision, a lot of the information that we obtain ourselves and process is done using light. So it is very important, not only to us as, organisms, but also to technology. And so I've mentioned a couple of these things, but obviously if you think about some of these new technologies that are becoming very widely spread, you're talking about things like autonomous cars, augmented reality I've mentioned before, remote sensing and wearables. A lot of them use light to probe the world around the object itself and hence provide us with additional information. And I'll come back to this because a key aspect of this is that we want to be able to miniaturise these components, and to do that we want to be able to miniaturise the ways that we control light, which means that there is a move away from conventional lenses, which are somewhat relatively chunky to what I'll talk about at the end. So if one thinks about traditional ways of controlling light with a lens, this is what's called the Nimrod lens. It's a few thousand years old and it was believed to be used for focusing light or potentially even using it for magnification. But if you think about a simple model of a lens that we use today, lenses in cameras, our phones, etc., basically the same concept. You've got some sort of transparent material with a varying thickness. And the thickness tends to be the order of millimetres to centimetres. So that distance is reasonably fixed by the requirement that that thickness variation actually controls the way that the lens works. And as I mentioned before, lenses are pretty well ubiquitous in smartphones. There are also additional components to some smartphones. So one of the higher end iPhones has LiDAR integrated into it, so it's actually sensing the world around it. We also want to be able to put optics into drones for agricultural and environmental sensing and other applications, and also into very tiny satellites that are being put up into space. And for these reasons, there's a lot of interest in being able to miniaturise optics, and so that's what I'm going to come back to at the end. But what we're going to start with is going back, way back, to the original understanding of light. And so for thousands of years, if we go back to the ancient civilizations from Greece, China, India, they had a reasonable understanding that light travelled in straight lines. And if we roll forward a couple of thousand years to Al-Haitham, who is often regarded as one of the founders of the scientific method, he formulated a lot of the fundamental principles that we now rely on for conventional optics. And there's a story, whether it's apocryphal or not, that Archimedes was able to use mirrors in the Battle of Syracuse to inflict damage on the Roman fleet. And you'd think by now people would have realised that you can actually focus light with curved surfaces. This is a building in London, and I think it was probably about a decade ago. They unveiled all of these lovely shiny windows, and they realised that it was actually focusing light onto the footpath, and it was actually causing a lot of damage. So they actually had to retrofit screens and things like that onto the surface of this building to address this particular problem. So we also know in terms of just being able to control light, to be able to focus light, to either deliberately or unintentionally cause some sort of damage, we can also form images with mirrors. And so if you think about the simplest kind of mirror, and if you're looking at yourself in the mirror, what is actually happening is light from an object, and this could be light from yourself, from your face, then travels to the mirror, is reflected from the mirror, and you perceive an image of the object sitting behind the mirror itself. Now, we don't have to have 100% reflective surfaces to create an image. And there are other types of materials that reflect light. So you can see here I have a beaker with another little beaker inside. And what you're actually seeing here is light reflected from both of those beakers, and it comes about because of the change in the refractive index between the air that's around it and the glass that it's composed of. So if, on the other hand, and I think Steve's going to dive in here near the camera. Oh, should I stand here?
Wrong one. Yeah, you just, yeah.
And if I put it back down there, what I'm going to do here is just fill this up here.
Maybe unscrew the lid.
I think I'll unscrew the lid. We'll be here all night watching me pour baby oil. And so we can no longer see that little beaker, okay? And what we've done is we've effectively index matched the glass of the inner beaker to the surrounds. So that means we've cut those reflections there. Okay, so we can get reflections from glass as well. And for that reason, we can also produce images using a flat glass or partially reflecting surface. So there is a phenomenon known as Pepper's ghost, and it is often referred in the entertainment industry as being a hologram. It's not a hologram. So they'll say, oh, you know, this thing is the hologram of ABBA, for example. Usually what they're doing is they're talking about using some sort of flat sheet of glass and either projecting an image from a projector, or if you go back to, you know, the 19th century, they could have someone sitting below the stage hidden from the audience here. They're illuminated, light travels up here and reflects that back out to the audience. So here we have some objects down here, light can travel from them. Now, with glass, some of the light is transmitted, but some of the light is reflected. So we've seen, so it's partially reflecting. And in this case, again, you're going to see the light appearing to come from some objects over here. So this is the phenomenon of Pepper's ghost. I'll get this set up over here. Now, Steve might dive in with the camera, but we are going to have to turn the lights down. So just a warning about that.
Be all the way.
Now the people in the front can probably see what we're looking at here. It looks like there is this ghostly apparition of these objects that are on the screen, and what is actually happening is that they are coming up and they're reflecting off those flat sloping surfaces. So this is Pepper's ghost, and Steve's going to try and get in here and get a look at it, and it is actually moving. It's a bit blurry there. It's focused on the edges of the... Oh, yeah, that's better. That's much better. Yeah. So it now moves on to this image here. And I think it actually looks quite beautiful for something that's a very, very simple effect. It's quite powerful. And you can see why it has this, you know, it is used. But just remember, it's not a hologram. If anyone ever tells you it is, it's holography is quite a different thing. Okay, thanks, Steve. I think we'll stop there. I might take this off just to avoid tempting fate. Okay. Of course, we can create images not only with flat mirrors and surfaces, but also with curved mirrors. So you'd be familiar with the concept of a convex mirror, and this is quite a famous painting on the left. And if you zoom in, you can see that the image is distorted. We can also have concave mirrors. And I'm not sure, some of you would be familiar with the concept of ray diagrams in traditional optics, but with a curved mirror like this, we can trace lines here, and what that means is that you'd end up with an inverted image, real image, of the object itself. When we're talking about the flat mirrors, the convex mirrors, the Pepper's ghost, we're talking about virtual images. With this concave mirror, in this configuration, we're talking about a real image. And I've got an example of a real image here. Of course, I can't see it from here. Can you see the... Okay, so it's... I can't actually see what I'm doing here. I see nothing. So I'm just waving my hand around. Okay, the people on the edges of the theatre, can you people see anything here? I'll tilt this around a little bit. Okay, and people over the far side, can you see it now? So this is a real image, and you know, I could turn this around. In fact, I might do that just to give the game away. Hopefully it won't. And you can actually see the original object. So what you're seeing before was the real image. And if I turn this around, you can see the original object is this upside down light bulb. Oops. I'll push it out here. Probably would have been easier for me just to turn the box around. Okay, I'll do that. Okay, so you've got the idea there. All right, now I've lost my pointer. And I'll turn this off. Okay, so everything I've been talking about so far can be described using what's referred to as geometric optics, this whole idea of light travelling in straight lines. But it became apparent when we started to get up to the 18th or 19th century that light had a wave aspect to it. And there were some famous demonstrations, one of which is Poisson's spot, named after the person who actually said basically this wave theory of light can't be correct because it would mean that you'd end up with a bright spot behind this opaque circular blockage. And the people to whom he said that went away and did the experiment and showed that in fact there was. So it's often, I think it's also sometimes referred to as Arago's spot, after the person who actually did the demonstration rather than the skeptic who made them do the verification. Okay, so light has this wave aspect to it, and I'm not going to go into details, but essentially what's waving here, we've got oscillating coupled electric and magnetic fields. And this, these electric and magnetic properties of light is actually integral to the kind of structures that we're actually producing. And these two animations here are showing, and I won't come back to this, but they're showing examples of what's called linearly and circularly polarised light. Okay, so what you think of as light is in fact the visible part of the electromagnetic spectrum, and I'll come back to talking about the spectrum later on, but we'd be familiar with the idea that different colours can correspond to different wavelengths of monochromatic light, and the colour is related to the wavelength of the light. And this is a little bit of a detour off into the photon picture of light and the interaction of light with atoms. But if we looked at, for example, some of my lines haven't come out here. I had energy levels drawn. But anyway, basically there are certain energy levels within atoms, and transitions between those energy levels as an atom goes from a higher to a lower energy level, it will emit photons with certain discrete and fixed wavelengths. And what that does is it actually generates a spectrum that is characteristic of that particular atom. And I'm going to pass around some, and I think there might be enough here, but I will, you can grab one, pass them around. You can grab one, pass them around. These are obviously glasses, and if we need more, I've got more. And what these do is they enable us to look at spectra produced by different light sources. So once you've got your glasses, you could probably just have a look at the, the lights in the ceiling, and I'm not sure what the lights in the ceiling actually look like. But yeah, there's some interesting things going on up there. Okay, so what I've got here are some lamps. Maybe drop the lights. Drop lights.
Maybe blank the screen.
Yeah, maybe blank the screen too. And if you look through the glasses, you can put them on. You should be able to see that there are some certain discrete, separate, bright lines appearing. Okay, you can see those. Some people in certain positions will be in a better spot than others, unfortunately. Okay, so what you're actually seeing there, and I'll show you what these glasses do, and I'll come back to this. This is a consequence of the wave nature of light and what's actually in your glasses. I have here a red laser pointer, and if I shine it through the glasses, you can see it produces these spots. And the positions of those spots depends on the wavelength of the light. So by having different wavelengths of light, you're now using these glasses to separate out those different wavelengths of light. Okay, so we think this is hydrogen, and I can change to different lamps here, and we can see different spectra, and I think this is helium. So you'll note that the lines you're seeing, can you see that they look different from before? And so this is a way of enabling discrimination between different types of gases. Obviously they have different colours, but this provides more complete information. And we also have what we believe is neon, and it produces quite a different spectrum again, and you can tell it's red, so that is obviously going to be producing different colours. So the spectra are giving us a fingerprint of the elements that are contained within these lamps. So you can keep these. Yep. And I have more if anyone's missed out or you'd like to take a few more back to your school. Okay, so we've been looking at these spectra. We've seen helium and neon. Mercury is another one with a very nice characteristic spectrum. And once you've got these glasses, you can go and look at all sorts of things, obviously not the sun, but other things, and seeing what's there. Now, what we've got here is quite a fairly primitive form of spectroscope. It enables us to split up light into its constituent colours. And another way of doing this is using a prism. But what a prism, the separation that you get between different wavelengths with a prism is relatively small compared to what you can get with something like this. And basically this is a grating. It's a type of transmission grating. It consists of obviously clear plastic, and it's got very finely ruled lines and cross shapes, if you like, ruled into it. And what that does is it leads to what's called diffraction. So we can use diffraction to decompose light into its constituent elements. So if you've got a flat surface, a mirror, you just get what's called specular reflection. If you texture that surface, so you've got some sort of periodic arrangement with a certain spacing there, the light coming in is going to be reflected, but that's going to depend on the the wavelength of the light. It's a little bit more complicated than that, but you can use these gratings to split light up into its constituent colours, and you can control the spreading of the light by changing the period, and that means that you can actually get a much better separation and hence a higher wavelength resolution than you would get with something like a prism. So spectrometers that are used today tend to rely on these sort of diffractive effects more than a refractive effect that's due to dispersion. And other examples, where's it gone here? I should not bother with this anymore, but some of you may be aware of the existence of this ancient technology called a DVD. If you have a look at this, you can see there's all these colours, but if you I'll come back to this. But if you had a scanning electron microscope, for example, and went and had a look at the surface of this, you'd see it had regular pits in it. It's not a perfect grating, like I tried to draw here, but it's the same sort of thing, and so it again produces this colour-dependent reflection. So the details of this separation for a given order in a diffraction grating, and in fact your little gratings that I've given you here are producing several orders here. So you end up with this term here that depends on the wavelength. So the angle of diffraction depends on the wavelength and the period. And the smaller the groove spacing, the larger the angular spread. So you can improve the resolution, as I said before, by having finer gratings. And here's a nice big picture of the DVD. And this is on the right, there is, this isn't particularly this, but this on the right, this is an example of what you might see if you used a high resolution electron microscope to see what's actually there. And these regular spaced structures in here are what are producing the colours here. So again, your DVD is acting a bit like a grating, could be used to split colour up into its constituents. Now I don't know whether you've had a look at the some of the items in the cabinets upstairs. We have upstairs a museum that's named after my late colleague Ed Muirhead, and there are items in there that are in fact diffraction gratings, because if you wind back 120 years or so, the ideas around quantum physics and looking at the spectra of different materials, these were at the cutting edge of physics at the time. So in order to participate in research, and members of this School of Physics were doing that, they needed to have access to gratings to be able to look at the light emitted by different sources. And so if you look in the cabinets upstairs, we have here, this is actually a grating, and if you go and have a look at them and move your head around, you'll see the separation into colours. And similarly, there's another one here. Okay, so they're both on display, I believe. This one here was produced in the United States by a very famous physicist called Rowland, but it became very apparent that if they were going to be serious about doing this kind of research here in Melbourne, they needed to make their own gratings. So being able to make gratings was something that was seen as really important to progress the science of the day. And this one up here in the top left, this was in fact made in Melbourne using this. Okay, this is just a nice looking section of a grating ruling engine that's about, it's a bit over 100 years old. It was made by a man called Edward Grayson, and he supported Sir Thomas Laby and actually built this grating ruling engine so they could actually produce as many gratings as they needed. So next time you're passing through that museum, keep an eye out. I love this one. It's all this beautiful brass, and you know, it's been beautifully machined, and it can produce very high quality gratings. Okay, now I've talked about, you know, ancient civilizations, but if we go back even further, nature uses diffraction to produce colours. So if you look at peacock feathers, if you look at any bird that has iridescent feathers, even a humble pigeon can produce beautiful colours. And if you look at beetles, some of the beetles produce these beautiful, you know, iridescent colours where if you look at them from different directions, the colours look different. That is a signature of a structural colour. And in the 17th century, when Robert Hooke built his microscope, one of the things he did is he looked at peacock feathers, and he was able to see these regular arrangements of structures within the feathers that were ultimately responsible for some of this beautiful colouring that we see. And in fact, now we're able to produce nanostructures in a reasonably reliable way. It's actually attracting interest for contemporary applications. So one obvious one that has gotten a lot of publicity is what's called structural blue, which is a colour that you could get in a Toyota Lexus. And it has been inspired by the colours of the morpho butterfly. And if you look at the butterfly wings in detail with the scanning electron microscope, you can actually see, again, these regular structures that are responsible for that iridescent blue colour. And one of the nice things about, well, there's many nice things about structural colour, but one of them is that it's very robust. If you think about, if you go and have, some sort of object that has been coloured using pigments or dyes, they tend to fade over time. But there's structural colour, as long as the structural integrity remains and the materials don't change, then that colour will last indefinitely. And there are fossil samples of beetles that still have that iridescent colour. So it just highlights just how robust structural colour can actually be. Okay, so moving on from colour, let's go back to looking at this idea of a grating. And what happens, we see that as the spacing gets smaller and smaller, these colours get spread out more and more, but eventually you get to a point where rather than seeing this kind of phenomenon, you don't see this diffractive effect, you just get the specular reflection occurring again, but the light has changed. The light that is reflected from that structure is no longer the same as the incident light. So its spectrum can change, so the colour could change. You can use gratings to produce very specific colours. Its polarisation could change, and the phase can also change, and I'll say a bit more about phase later on. So, and I've tried to come up with this idea of a grating that's just these bunch of lines, but in fact you can have periodic arrangements of any sorts of structures, and some of them look really bizarre. So people in my group are actually using optimisation, machine learning kinds of approaches to actually design these structures, and some of them look really random, but they still basically have this property of being a periodic structure. Okay, so let's come back to thinking about, well, how you would go about, rather than having a conventional lens, can you make something that's a lot smaller, a lot flatter? Go from having a lens that has a typical thickness of, say, 10 centimetres or even millimetres or so, but still relatively thick, and reducing it down to the size of, say, 100 nanometres or so. Okay, orders of magnitude thinner. And this would enable you to significantly reduce the size of electronic devices, such as phones, that rely on optics to form images. Okay, so a structure like, the way this can be done is basically you create a whole lot of resonators, okay, and those resonators interact with light in a characteristic way, and doing that you can actually create lenses of different kinds, and I'll come back to this as well. And if you can do this, you can make these really flat structures that can be integrated into portable electronics. They're much lighter as well, and so they're much more compatible with systems like drones and satellites where weight is critical. Okay, so if we zoom in on one of these structures here that might make up this meta lens, you can see that this is a model showing what the electric field looks like in there, and you can see it has this characteristic pattern. And I want to start talking about waves, because essentially what we're looking at there is some sort of resonance of this structure. It's an optical resonance rather than a sound resonance or some other kind of resonance. Okay, and before we go on, I'll say a little bit more about how lenses can focus light. So this is an animation showing light coming in. It's interacting with the lens, and you can see that these flat wavefronts coming in get curved around when it passes through the lens, and it's focused down to a point here. And the way this works is that the lens has a varying thickness. Okay, so it's thin up the top and thick down the bottom. And so that produces a delay of the light propagating through the middle, so it slows down a bit and leads to this bending of the light passing through it and ultimately to focus it. But to focus light this way requires a certain thickness. And I have here a demonstration. Again, just highlighting what's happening with the lens. I'll turn the lights off just to highlight this. Oh, we need smoke, don't we?
Yeah.
We get some smoke going. Okay, so the varying thickness of that lens produces that variation in phase, or the different parts of the beam, or different beams here are passing through different thicknesses of the lens. Okay, and that ultimately produces focusing. Okay, so thanks for that, Steve. That was very brief excursion off into talking about lenses. But we need to be able to, if we want to be able to focus lens using some flat thing, we need to come up with some alternative way of introducing that kind of phase variation. Okay, and one way of doing this is, as I said, I've alluded to a couple of times, is to use the concept of resonance. Okay, if something is resonating, and that's what you'd see with a tuning fork, imagine that this tuning fork that has this size is resonating. And then think about, well, what would this same light be? This, we're making some sort of sound that's interacting with these tuning forks. This one here would be, for example, on resonance here, but these ones here, these shorter ones, are going to have a different resonant frequency than these ones over here. So they will either be below resonance or above resonance. And what happens when you have different resonant frequencies is that there will be a different phase. And so by having structures with different sizes, some of which are above resonance or below resonance, we can actually manipulate the phase of the wave that is interacting with them. So in practice, you would never do this, use tuning forks to manipulate the behaviour of sound waves, but you can imagine something like this could be used to actually deflect sound waves in a given direction. So I want to say a little bit more about the concept of resonance. Just double check where I'm up to here. And so I've got a couple of demonstrations here, and I don't have Steve. Oh, I do have Steve, right. Where's the light? So we can have, this is a resonance of a mechanical wave that we're going to look at here. Okay, so I'm just going to increase the frequency. And you can see that I've wound it up. What I've been doing is changing the frequency, and I've now identified a frequency that corresponds to a particular mode of this piece of string. And I can increase the frequency. I've just got to find the right frequency. You can see I'm slightly off it. Oh, here we go. This is another mode. You can see it has a different shape. I won't go into details here. And I can keep... And here's another mode. So this system here has certain characteristic modes. And I have another one here. So this is a mechanical wave. And a warning, I'm about to make some bad noises.
And the other one.
Okay, so again, we're talking about a mechanical wave here, but rather than being one-dimensional, it's going to be in a two-dimensional circular plate. Some of the noises here, I'll try to keep it as low as possible, but to see an effect. And so you might want to cover your ears at certain points. Okay, so you can see there's a pattern there on the surface. So that's a mode of that plate. And the salt is settling in the parts of the plate that aren't vibrating up and down. Let's see if I can find another one. Things get more painful as you go to higher frequencies, I think. And there's another one. Okay, so there's a whole zoo of these modes. And look, one thing to note is that the frequencies that I'm required to drive these at depend on the size of the plate. If I made the plate bigger, the relevant frequencies would be lower. If I made the plate smaller, I'd have to go to even higher frequencies. If I made the string shorter, I'd have to go to higher frequencies. And this is going to be important because, remember, I'm talking about light. The wavelength of light is very low, the frequency of light is very high. So think about the sizes of the structures that you would need to be able to create things that resonate optically. Okay, yeah, turn that off. Thanks, Steve. Okay, so coming back to the using phase to manipulate sound waves, people have in fact created a series of acoustic resonators. And so they look like these cylinders here, and they've actually made a lens that actually focuses sound using a system that looks like that. So because we're talking about sound waves and the wavelength of sound waves is relatively large, the lens itself is actually quite big. But if we want to do something like this optically, it's going to have to be a lot smaller. Okay, so I'll come back to this. So I've mentioned it before that light is a wave. It's an electromagnetic wave, and it we describe them using different words depending on the relevant frequency or wavelength. So very short wavelengths, we've got our gamma rays and our X-rays and ultraviolet, and at longer waves we've got infrared, microwaves, radio waves and so forth. And our visible spectrum just sits between ultraviolet and infrared radiation. And typical wavelengths in this region here are of the order of hundreds of nanometres, just to give you an idea of scale. Okay, so I want to spend the rest of my time talking about meta-optics. And the first concepts regarding meta-optics related to things called metamaterials. And the name came about because when one thinks about the optical properties of material, generally what you're talking about is the way that light interacts with the atoms and molecules of which that material is composed. On the other hand, metamaterials are derived from the structure, okay, in the same way structural colour relates to structure rather than, you know, atoms and molecules. Okay, so, and when people became very interested in metamaterials, some ideas they were interested in were creating materials that had a negative refractive index, for example. And that required what's called a negative permittivity, so an array of wires, and a negative permeability, so this negative response to an applied magnetic field. So that consisted of a whole lot of loops. So there was a lot of interest in being able to demonstrate what's called negative refraction. And if you have light that goes from air, for example, into water, you would see the wavelength of the light changing, and you'd also see the direction of the light bending. And I think a lot of you would be very familiar with that phenomenon, described by Snell's law. Okay, so this simulation was done assuming the top material had a refractive index of 1 and the bottom had a refractive index of 2. And if we do the same simulation, but I assume the top material has a refractive index of +1, but the other material has a refractive index of -1. So this does not occur in conventional materials, at least not at optical wavelengths. But if you could create that material, you get negative refraction. So rather, the actual direction of the light reverses with respect to the normal to the surface. And it actually looks like the light is travelling up here, okay, but in fact the energy is in the direction of that arrow. So it's actually quite a weird thing. And so this attracted people's interest, and so there was a lot of people working on being able to demonstrate this negative refractive index. And it wasn't just a purely, a purely hero demonstration. There was an underlying motivation for doing this, and that was to create what's called a perfect lens. I won't go into the wave optics that describes that you can't have a perfect lens, but there was interest that if you could create a slab of negative index material, you could actually take an image of a point on one side of that material to a perfect image of a point on the other side of that material, just using the properties of this negative refractive index material. Okay, so this is just showing where the rays would be going. So you don't have to worry about diffraction in this case. And so the early demonstrations of metamaterials, and we're going back to probably about 25 years ago, a lot of the early demonstrations were done using microwaves. And typical sizes of the wavelengths there of the order of millimetres to centimetres. So the scale of the objects that you needed to manipulate electromagnetic waves at those wavelengths were relatively large. Okay, but if you want to do things in the visible, you have to go to much shorter wavelengths. Another thing that got people very excited was the idea of cloaking. Now, I've showed you how I could make that little beaker disappear, but what people wanted to do was to create this device that would basically steer light around an object inside it, hiding it from an observer. So not only do you need to stop the reflections, but you also need to make sure that light is not being bent in a way that reveals that there's actually something inside. So this was the idea of the electromagnetic cloak. And this got people very excited for a while. It seems to have simmered down now, but there were all these, newspaper articles, popular press articles with, Harry Potter pictures and things like that. But this was one of the first demonstrations of this, and again, this was done with microwaves. So the wavelength at which this experiment was done was a few centimetres. Okay, so so this was all very interesting. But as I mentioned, we want to go from talking about things that have wavelengths of centimetres down to the visible part of the spectrum, several orders of magnitude. And if you want to be able to do these kinds of things and make things invisible, make cloaks, make perfect lenses, you need to start talking about things on the nanoscale. And just a reminder as to, when I start talking about things that are the size of the wavelength of light, I'm talking about things that are slightly bigger than viruses, smaller than bacteria and cells like that. So we're talking about things that are very much submicroscopic in scale. So people have been making metamaterials, and there's a variety of different strategies that people have employed to fabricate them. And There has been a demonstration of a perfect lens in the ultraviolet, so this had negative refraction, and they were able to actually demonstrate this particular device. But in fact, the whole idea of metamaterials has really spawned interest in how we utilise the interaction of light with matter that's structured on the nanoscale. And the area of meta-optics falls into this. We're trying to manipulate light through its interaction with nanostructures. And again, there have been a lot of devices, and these are some examples of the sorts of shapes and structures that people are interested in. So, you know, using a structure that looks like this, a whole lot of little nanospirals to produce circularly polarised light. Creating a structure like that that will bend light, okay? Rather than having to have a prism, you could actually just bend light with a flat structure. So these are typical sorts of structures that people are interested in. An example from some work in my group involved just a demonstration of how one might go about producing these nanostructures. So we use one technique to make a mould. Okay, I won't go into the details of that, but once you've got this structure, you can actually emboss, basically stamp a structure into a polymer, and doing this and then coating it with metal, and then we're able to generate all of these colours using this particular approach. So it created this amazing colour palette, and if we change the polarisation of the incident light, we actually change the colours. So again, that's another thing to do with structural colour. So metasurfaces are basically what I'm working on now, one of the things I'm working on now. And these are some examples of the sorts of structures. We have to use a scanning electron microscope. We can't use an optical microscope to actually look at the structures because they're very, very tiny. And you tend to see structures that are made out of metal. They can also be made out of things like silicon or other dielectrics. And the whole idea of these structures is to control light in various ways. And that includes actually focusing light with an appropriately patterned surface. And in fact, this, I think, slide basically shows what they're trying to do here. Go from talking about something like this down to a structure like this. So again, we're talking many orders of magnitude thinner, and rather than talking about the light being controlled by how thick the material is that it's passed through, to now interacting with a whole lot of little optical resonators, okay? So rather than sound driving these plates, for example, or you know, vibrating them mechanically, we're actually driving these resonators with light. The electric field in particular in an electromagnetic wave that light is an example of will actually lead to resonances of these little structures, and you can use that to focus light rather than having to have objects with different thicknesses. And so there's been a huge interest in this, and you can see essentially you've got all these little structures here. This is what your little resonators look like, and you're controlling the shape to focus the light. So that is essentially one of the key you know, activities when we're thinking about looking at meta-optics. Okay, so Marion mentioned I'm part of this Australian Research Council Centre of Excellence for Transformative Meta-Optical Systems. We're a consortium of 5 universities. It's led out of the Australian National University. We are a node here at Melbourne. There are also nodes at University of Technology Sydney, RMIT University and the University of Western Australia. And so our mission is looking at different ways to generate light, so integrating emitters of various kinds into these resonant structures and controlling the emission. We're interested in manipulating light, and meta lenses falls into that category. And we're also interested in utilising metasurfaces to extract information from light, because light carries an enormous amount of information. So these are our key goals here: to discover new ways of utilising light-matter interactions, to develop new kinds of devices and to investigate translation to various applications. And the sorts of things that people in my group are looking at, we have a strong interest in structural colour, and that extends to a collaboration with the School of Biosciences here, looking at structural colour in beetles, which is fascinating, and also many beetles actually change the polarisation of light, which is quite fascinating. In terms of structural colour, I don't have it here because it's hot off the presses. We had a paper come out earlier in the week looking at how we can use little cavities that are resonators, and cavities of the right size will produce certain colours, but if they trap nanoplastics, then the colour changes. So we've actually demonstrated that you can use these little resonant voids to show the presence and also the size of various nanoplastic particles. And this is done just by looking at the colour that is produced by this object after it's been put into some liquid water that contains nanoparticles. So structural colour has a huge range of applications. We're also interested, and I mentioned trying to get information out of light. The phase of light carries information that's very hard to see. So, for example, we designed this grating structure here, and we also created a kind of arbitrary phase variation that's meant to look a bit like a red blood cell. And if we just tried looking at it with a normal camera, you can't really see anything there. But then if you put this grating structure in front of the camera, you can now see this. And so this is what you're doing if you want to look at unstained biological cells, such as HeLa cells. That's what we're looking at here. These ones over here are sitting on top of this grating, and these ones over here, there's nothing there. So being able to visualise things that are otherwise invisible is one of the things that we're very interested in. And that brings me to the end. So essentially, I hope you've got the idea that we're looking at the synthesis of nanoscience and optics. And basically, it's going to underpin the next generation of optical devices, and because they're so small, they're going to be highly integratable into a range of devices. And in fact, they're going to be so small that you probably wouldn't even be aware of their presence. There's a whole lot of really interesting physics in there in being able to harness light, and hopefully you've got the idea that we're utilising ideas that are more commonly associated with things like mechanics and sound, this idea of resonance, but now we can scale it right down to the nanoscale, and when we do that we can actually create these optical resonators and make a whole range of really interesting devices. And so my little parting comment there is that the future is meta. So thank you. So, any questions? I realised I forgot a demonstration.
You mentioned that perfect lenses have been demonstrated for UV light. The wavelength of UV light is shorter than that of visible light. Has the same thing been done with visible light? Could it be done?
Potentially. Actually, the UV came up, I think it's the nature of, they just had the exact right materials, because again, you've got to deal with get the properties of the materials exactly right. And I didn't talk about the details of the structure, but that was one where they're just using a multi-layered kind of structure rather than something that's got some sort of pattern in it, like some of these other ones. So yeah, but they were just trying to get this bulk effect there. Yeah, so I'm not sure whether I haven't seen a lot written about it lately, and I'm not sure if that's just because everyone's moved on, it's been demonstrated, or whether it's become quite difficult. But yeah, that's a good question. Yeah, it does seem anomalous to me that the UV, but UV is an area where it's hard to get, good lenses, for example, because of the way that it interacts with light. Yeah. Any other questions? There's one here.
What is the negative permittivity probability? Do some materials just have that, or do we have to produce materials with that characteristic?
Okay, so not at the sort of optical wavelengths, and even at longer wavelengths. I think if you go to very long wavelengths, like deep into radio waves and things like that, there might be some materials that exhibit unusual properties. But in the the visible part of the spectrum, no. So you have to go to artificial materials for negative permeability. But for permittivity, yes, there are metals will exhibit a negative permittivity. Yeah. Yep.
With the surfaces that have the green on them, is there a way to have it exhibit a constant colour? Because if it diffracts the light, doesn't that mean that if you look at it from a different angle, it will be a different colour?
It's a very, very good question. So one of the aims is if the period is small enough, you can actually design it so that it doesn't, even if you're coming in at an angle, you're not going to see any change. But generally, as the angle gets bigger, you're more likely to get diffraction. So then you will see some other things going on. One of the things that we're looking at, this business of being able to, see invisible things, we're actually trying to make it depend on the angle. So how much light's going through depends on the angle. But yes, so the phenomenon you're talking about there is iridescence, and that's so when you're looking at the beetles, for example, from different directions, you'll see the colour changing in that particular case. But yes, if the period is small enough, you won't see that. But as the period gets bigger, it becomes more and more apparent as you go off normal.
So when the period's small, it's still it's the same concept. It's just the diffraction's so small.
Yeah, so I don't want to sort of say scary things, but what happens is those waves that you would otherwise see, because if we go back to, where's this thing? What we're seeing here, I'll turn the lights down. Okay, what is happening here is that this isn't reflection, so we're doing this in transmission. You can clearly see there's the central spot, and there's these other spots around it that they're what's called diffracted orders. As the wavelength gets longer, okay, so relative to the wavelength, the period gets smaller, those spots will get further and further away. They'll be travelling out at bigger and bigger and bigger angles, and eventually that angle turns into 90 degrees. And then beyond that, they are what's called evanescent waves. So they actually, they're very interesting waves, but they're not carrying energy away from the surface. Does that make sense? Yeah. Are there any other questions? I'll turn the lights back on. Yes.
Does the perfect optic address the problem of chromatic aberration that it only works for a certain type wavelengths?
Yeah, so the perfect lens, I'm not sure, we talked about perfect lens before, I'm not sure where that's going. There were some, I think people started to realise that to make a perfect lens was although theoretically possible, was in practice very challenging. Also, it did assume that the thing was infinitely big and things like that. And also, if you're relying on resonances, you remember they are going to depend on the frequency, the wavelength. They're going to be, as you say, highly chromatic. But also all of the meta lenses, or some of the meta lenses, again, depending on if they're relying on resonances, there will be chromatic effects. So a big area of research is looking at reducing chromatic aberrations, and there is a non-resonant way of doing of manipulating light using polarisation that I haven't talked about here, but there are other ways of actually manipulating light using these sort of structured surfaces as well that are much more broadband. But even in the, you know, chromatic aberration is even more of an issue there. But there are other clever things people do, and they could, for example, make interleaved red, green, blue type lenses that all have the same, they're interleaved with each other and all have the same focal length. So they can do clever things like that you couldn't do with a conventional optic. Yeah, I think there's still a way to go in. I think some, there are, well, there is, I heard there was a phone that actually had a metal lens in it, but more for the facial recognition rather than for producing, you know, nice pictures with your phone. So there's a lot of things done with lenses that aren't just about creating images. They're used for other applications for which some of these lenses might be better. Yeah, does that answer your question? It's a very good one. Yeah. Other questions? Yes?
You briefly touched on this at the end of your previous question, but your parting remark was the future is meta. How far away do you think these meta optics are from being integrated into our everyday lives?
Okay, so I mentioned, I believe there are phones that have, as I said, use a meta lens because it's a much more compact thing, but not for the, you know, producing high quality images. And you know, there are quite large companies that are investing quite heavily in this. And, you know, there's also, I mentioned at the beginning, things like augmented reality, and I think they're going to have to go to these very compact optical components because nobody's going to want to walk around wearing chunky glasses. They'll really want very flat optics. And that's become, it looks like that sort of thing's become a bit of a destination for people that have done PhDs or worked with me. Because they've got the right sort of skill set. So it's, yeah, interesting. So look, there's a lot of activity in this area, and there'll be certain niche applications, I think, where they'll be used first rather than, you know, other ones which, you know, really, really good cameras, for example. I can't see them being in those for a while. Because, and you know, some of these amazing microscope objectives that we use for high-end microscopy, again, the technology in there is very complicated. Yeah. Yes?
Structural colour, is that sort of possible now and economically viable? Where are we at with actually making things?
Again, I think you're probably not talking about making cheap things, but again, you can emboss. That was the purpose of the work they talked about there, the fact that we could emboss surfaces with colour. And there are, as I said, there's the car is the classic example. It uses a structural coloration and it's been incorporated into a pigment. But yeah, and another, I think it's used in things like security features because you've got this potential for polarisation dependence that normal pigments don't have. So yeah, so there are, I should have a better answer to that.
It just sounds fascinating.
It is, and it's, and the other thing I didn't mention is that you can, well, the fact that beetles can have such vivid colours and they're made out of, you know, obviously, you know, naturally occurring materials. So there is a sustainability angle to that rather than using chemicals to produce colours. Is that it? Okay, well, might, what time is it? Okay, it's 22. Okay. All right, well, thanks for coming along. It's pretty cold out there. Hope you don't freeze to death going home. You're very welcome to come down and have a quick look at some of the demonstrations here. Obviously, Steve needs to get out the door. And particularly this one here that I forgot to show you, which is very cute. It is, shows you that you can generate multiple images just using simple flat mirrors. It's very pretty and kind of cute. So again, depending on where you're sitting, you may or may not be able to see things. Okay. Thank you. Thank you, Steve. Did I forget anything else? That's all right. If anyone wants any more, oh, I've got some stickers, if you like stickers.
Spare these.
Oh, you want some? Oh, you got spare ones and glasses?
Thank you.
Got some nice, Thank you. That's very interesting. Yeah, I'm never sure about the structure of it. I'm trying to tell several stories at once. Well, it's good to like history and everything. Yes, my name. Actually, I think it's Anne Roberts. A-N-N. Yeah, sure. How many do you want?
Just two, I guess. I was thinking, like, if you have a normal light, to be honest, I wanted to use these to make some cool effects in my room, like in light. So if you put like a light behind this, it would have a similar effect.
I'll show you. Phone's interesting.
Yeah. So like just be able to see it on the wall.
Yes. So if I just grab my flashlight. The light is being used by camera. Now, if you look at it from the other side.
Oh, and did this show up on?
You'd probably have to be dark enough to. Actually, we could drop the lights.
Oh yeah.
You'd have to. It's going to. Yeah, but the lights all recombining again. So yeah, you'd have to image it somehow. Yeah.
So,
but it looks good from the outside.
Is it because it's like?
It's coming out, but it's all, yeah.
It's getting
just,
separated.
It's all just spreading out
It's
and going.
spreading out, but there's other things that are also spreading out. So, so if it was like a white laser, then it would be split nicely.
Yeah, if it was very collimated, you could probably do that, what we call collimated.
Okay, cool. I'll have a
You never
exploration.
play.
I will really.
I think you can buy sheets of this plastic
looking
stuff without
online.
all of the, the glasses.
I was looking online for them, but I didn't know where to
Start. Look for, I guess sometimes they might call it holographic sheets or grating sheets or something like that.
Okay, yeah. Thank you. Did you look at that one?
It's just for recipe.
Let's grab mine. Please.
Thank you. That was very enjoyable.
Oh, well, thank you for coming along.
Yes.
Night Nor. Yeah.
Yes.
And the questions, yeah, they're good questions. Caught me out a bit. Yeah.
Oh, I try where I can to learn as much and find out about these
I can
things.
see that. Yeah.
How much people? You said there was a lot of